In this fifth and final video about the data link layer, we will discuss media access control or contention control in token ring networks. Token ring networks are in principle very simple networks to build because you have a ring topology and you pass a token from one node to the next, to the next, to the next. That gives one a feeling of safety that you will eventually get that token and then you will be able to speak. It sounds very different from what you had in multiple access networks where there was almost chaos. Anyone could talk at any given time. However, token ring networks did not survive. Multiple access networks did survive. This was due to many factors. One of them was the cost of token ring networks. The other one was the fact that multiple access networks worked and they were being developed actively and they got faster and faster. And because of their popularity, they became more popular. In token ring networks, you will see that we will discuss the basic notion, and then we will find a problem why this basic notion is flawed. And then we will fix that, but then we will find a flaw in our fix, and we have to fix that. So to study what's going on in token ring networks, one has to understand it as a series of problems that were corrected, but that caused other problems and that were corrected. Now, this is not the way in which token ring networks really developed, but it's a nice way to think about it from a logical perspective. Often it's easier to visualize something if you can actually see it. So since we're going to talk about a ring, here is a prop that we can use as our ring. Just a piece of rope. And what we're going to do is to add our computers to this ring. So there may be a computer connected to it, and there's another one that is connected to it, and a third one, and a fourth one. Now, what token ring will do is it will pass the token. Let's say this yellow one has the token at the moment. We've already seen the token when we spoke about data delineation. But let's say that this one has the token at the moment. And it sends that token to its neighbor. What this means is this neighbor is now allowed to speak. And the neighbor will remove the token from the ring, and the green one will send its message right around the ring and until it returns to the green one. Now, let's say that the message that this one is sending at the moment, the green one is sending, is intended for the blue one. What will happen is the green one will pass or will forward the message to the purple one. The purple one will forward it to the blue one. The blue one will say, that's for me. I can see my MAC address there. And it will copy the message from the ring, and it will even flip a bit in the message on the medium. So when this medium is now forwarded to the next one in line, to the yellow one will say, that's not for me, and will forward it. And the neighbor of the yellow one is the green one, gets back to the green one, and the green one knows that my message has been delivered. The recipient got it because that bit is flipped, or alternatively, if it returns without any change, then it means it was not delivered, and that is a problem that it has to sort out later. But now that the green one has had the opportunity to send a message around the ring, it will forward the token to its next door neighbor. Next door neighbor was that one, the purple one, and the purple one is now allowed to speak. Message right around the ring, message forwarded to the blue one, right around the ring, message forwarded to the, and so on. So very nice, organized in the sense that whoever has this token is allowed to speak, so retains the token and sends a message right around and then passes the token to the next door neighbor. Now, one way you should think about this, even though it looks like a ring, it's really a connection between one node and another node. And then there's a connection from that node again to that node. So one of the challenges that introduces is the following. Suppose you want to go home. Been a long day and you've done enough. And you switch off your computer. And suddenly the ring is broken. And no one is able to talk. That can't work. We can't live like that. We need a solution to that. So let's quickly sort out that problem. And to visualize it, I'm going to use a little piece of wood. You can see nothing there, no trickery going on. And a couple of nails and some hardware. And and there you can see our layout that we're going to use to thread our ring around. So no change in the ring whatsoever. We're just going to use a somewhat more interesting layout in terms of how we arrange this ring. And there we are, a ring arranged somewhat differently. And what we're going to do next is to put this into a little cabinet of sorts, a wiring hub, and what you will then have is essentially a pair of wires running to the computer so that signals can come from this wiring hub to the computer, and a pair of wires going back to this wiring hub, keeping everything together. Okay, so let's quickly install the computers. And there they are, nicely laid out, again connected to our wiring hub. How does this solve our problem? Our problem previously was if somebody went home and they switched off their computer, then the ring was broken. This wiring hub is a pretty dumb piece of electricity, and if we disconnect the computer now, it would seem as if it is suddenly broken, but the wiring hub is has enough intelligence to say, okay, there we have a problem, let's make a connection, let's bridge that connection. So the ring simply goes through those three computers now. This one is cut out. If this one were to rejoin, then it would open up that connection again. As you can imagine, it's a pretty simple thing to build a piece of electronics that when there's electricity flowing through, then it keeps the circuit open. Whenever there's no electricity, when the circuit is already open, it's broken because the computer is switched off or whatever, it just sort of short circuits, it just makes another connection. Now, that's what it looks like in the abstract. In the real world, this is what a wiring hub looks like, and we will explore these sockets in a bit more detail. When you peer into that socket, you will see that there are 4 connectors, 2 pairs. Now that's exactly what we expected. You will have 2 wires going out from this hub to a node, and you will have 2 wires coming in from the node to the hub. So one piece of wire going out containing 4 strands of wire, 2 of them used for talking towards the hub, and 1 for talking from the hub. So whenever there's nothing plugged in or the connection is already open because the computer is switched off or it's plugged out of the computer side, then the hub will simply make sure that it bypasses that socket in the ring that is formed inside it. If you look at the hub from a slightly wider angle, you will see that this particular one has 8 sockets, and at the ends there are 2 sockets that you can use to connect this to other hubs. So if you want to increase the size of your local area network, you can do so by adding other hubs to this. While I was discussing the wiring up, I referred to the places where one could plug a cable in as a socket. But there's a pretty standard way of thinking about sockets and plugs in the electronics industry. Sockets are generally considered to be female, plugs are generally considered to be male for obvious reasons, and designed to make a connection in the obvious manner. In the case of the sockets that we saw here, sockets in quotes, game is a little bit different. Here is what would then be a plug and a little bit of a safety mechanism to plug it in. I have to be able to push those ends in, remove that, and I can suddenly push it in to open it up. And to plug it in, I simply push it in and make the connection. And there it clicks into place, and I can install the safety mechanism again. And what you will see is that we've got a very sturdy connection. To unplug it, remove the safety mechanism, and I can unplug it. Now, what makes this so very different from the usual plugs? Here I have another plug, again, safety connector removed, and I can take these 2 plugs and I can connect them together. So these plugs are not gendered. Marvelous piece of engineering where a plug can go into a socket, but a plug can also go into another plug. And the technical term for these are hermaphroditic plugs, or sockets if you prefer, hermaphroditic connectors to be precise. The problem that we've solved by now is the one where the ring is in a sense broken because someone switches off their computer, someone goes home, and as we've said on a couple of occasions now, the wiring hub solves that problem by simply bridging the connection to the link that is no longer in use, to that station that is switched off or unplugged, or even if it's an open socket. It's time to think about what can go wrong now. So as a reminder, how this protocol works, this token passes around the ring, and whenever someone gets a station, whenever a station, a node gets the token, it is allowed to speak. Challenge is, what if that token gets lost? Because then nobody will get the token and nobody will be able to speak. In terms of how a token may get lost, someone may switch off their computer, unplug it exactly the moment when it has the token, and the token is gone with the computer that's been switched off, and there's no token left. Or it may simply be a case that it is fully operational and lightning strikes, and it damages the token beyond repair. So it may have been traveling there and then lightning struck and token no longer looks like a token, and nobody will get the token, and therefore the network is quiet, no one can talk. How do we solve that? To solve the lost token problem, you clearly need something that will regenerate the token whenever it is lost. And an obvious thought would be, well, maybe the hub in the middle can regenerate the token. But as we've said time and again, that hub is a dumb piece of electronics, very old 1960s electronics. We can't trust it to do something as intelligent as that. So what happens rather is that one of these nodes gets appointed to be what is known as a monitor. And the responsibility of the monitor is to regenerate the token whenever the token is lost. In the setup, let us think about this node as the monitor at the moment. So with the token passing around the ring, the monitor will know that every so often it should see the token coming past it. Exactly how long, well, that may depend on a number of factors, for example, how big the packet sizes are and so on. But it's pretty easy to set up a maximum. So within a certain time limit, it should see the money, or it should see the token coming past. If that time has passed and it's not seen the token coming past, then it will regenerate a token. It will issue a new token and start passing that around the network. So that solves the lost token problem. Just think about the chaos if anyone were able to create a new token, because you may end up with multiple tokens and then nodes will be speaking across one another, and we can't tolerate that. Now, in our solution for to get a monitor on the network, we've created another potential problem, a single point of failure. Again, suppose this is your computer, you decide it's time to go home, you've done enough work for the day, and you go home. And now there's no monitor on the network. We specifically did not want a single point of failure. So that what the monitor will do while it is still active on the network, it will every once in a while send a message around the network to say, active monitor present. Don't worry, I am a monitor, I am on the network, so if the token gets lost, I will regenerate it. Whenever it disappears, then that message that says active monitor present will no longer be sent. And the other nodes on the network will become anxious. They haven't seen that message in quite a while, and they therefore have to elect a new monitor amongst themselves. Any station that sees that the monitor is missing can call for an election. If this station, let's say the traffic flows around the network in that direction, then if this one notices that there's no active monitor, or has been no active monitor message for a while, it will send a message to its neighbor to say, let's have an election. If this one notices that no active monitor messages have been sent around the network, it will inform its neighbor. And if that one notices that no such message has been sent for a while, it will inform its neighbor. So somehow or another, stations will either notice that no such message has been sent around, or they will be informed. Their neighbor will inform them that there is a monitor missing, we need to have an election. In terms of calling for this election, they will use what is known as the Bully algorithm. Bully, because the largest one is going to win. Largest one in terms of what? Largest one in terms of MAC address. So the one with the biggest MAC address is going to win this election. So during stage one, the various nodes, to get a somewhat more complete network again, let's say this is the situation at the moment. We've got our network, and there are 4 nodes on it, but none of them is the monitor. Then every station will inform its neighbor that an election is called for. That's phase 1. And then once everybody knows that an election is called for, a station will share its MAC address with its neighbor. The neighbor will, now obviously there's nothing coordinating this now, so a station has to sort of move on its own and talk to its neighbor. And maybe that neighbor is talking to that one, and that one is talking to that one. Who happens to talk first and who happens to talk last, and whether it's simultaneous or not. Nothing matters really. This cannot be controlled. So a station will inform its neighbor about its MAC, and then every station will compare the MAC that it has received with its own MAC address, and it will send out the larger of the two to the next neighbor. This neighbor will also compare its own MAC to what it has received, and it will send the bigger of the two. So at some point, every station will have received a MAC, compared it with its own MAC, and will have forwarded the MAC, the bigger one of the two, to the next station. After this round is completed, there is a station that will know that the MAC that it has received, the biggest MAC that it has received, is its own. And if it happens to be this particular one, then this one will announce itself as the winner. So this largest MAC will be sent around the network just once more. At that point, this node will see that it has the largest MAC, and voila, it's the winner. Being the winner in this election means this node has to do some work. So what this node is going to do, first of all, it's going to tell everybody that there is now an active monitor present. And the second thing that it will do is it will start watching the token, start monitoring the token. And if it sees the token every once in a while, within those regular intervals, fine. If it doesn't see it, then it knows the token is lost, and it will therefore regenerate the token, and you will have a new token, and the network is working perfectly again. One of the advantages of the protocol that we've just described is the fact that every node knows with certainty that it will get a chance to transmit. This token will be at one node. That node will send its data, which has a maximum size, and then it has to forward the token to the next node. And that node can then transmit again up to a certain limit, maximum packet size, and then it has to forward the token. We've looked at these eventualities where the token may be lost or where the monitor may be lost. But that's not going to happen very often, and the problem will be solved by the mechanisms that we've described. Given all of these advantages, one would have expected that this protocol would have been the winner in the local area sphere. However, one of the things that it had against it was the cost of this technology. I remember when I built my first computers with networks, I would go to my local computer store, and the network interface card for Ethernet would cost about 100 Rand. And at that time, that local computer store also sold a network interface card for a token ring network, and that would cost about 250 Rand. So clearly it was much more expensive to build token rings. And as we noted in the previous video, Ethernet just worked. It seemed we didn't have the problems that we expected. So the cheaper technology is the one that won this race. However, before leaving Token Ring, there are a couple of additional features of Token Ring that we have to mention. Token Ring makes provision for stations to have priorities, and a station can reserve the token. So when a data packet goes around the network, a station can put into that message that's going around the network something along the lines, I have priority 4, and the next station that should get the token is a priority 4 station. So when the token is then forwarded from whichever node has it, it will be marked as intended for a priority 4 node. And it will travel until a priority 4 node gets it. It may not even be the one that reserved it, but only a priority 4 node can then grab it and start transmitting. At the moment when you bring such priorities and token reservation in, then you lose your ability to guarantee everybody a chance. Because if 2 high priority stations keep on reserving the token, the low priority stations will never get a chance to speak. If you don't have to assign priorities, and all stations can have the same priority, and that means you can ensure that everybody will indeed get a chance. We mentioned in an earlier video that the IEEE standardized the IBM token ring as standard IEEE 802.5. We also mentioned that 802.4 was a standard, and that standard is based on the notion of a token bus. It works the same as a token ring in the sense that you need a token to speak, but it differs from a token ring in the sense that all stations are connected to a bus rather than a token ring, or rather than a ring topology. In principle, the token is sent from one machine to the neighbor, to the neighbor, to the neighbor, and so on, in exactly the same fashion that it is done in token rings. And then pretty much everything else works like it works in a token ring. The challenge comes in, who is your neighbor? In a token ring, the neighbor is determined by this physical wiring from one node to the next in a ring topology. However, on a bus, when there's a node plugged into the bus, then the other nodes don't know where it is plugged in, doesn't know how to find it. And what needs to happen is when a node on that bus becomes active, it has to inform the other stations on that bus that it is now present and that it should be included in this logical ring that is, in a sense, imposed on the bus. So that when this token is passed from station to station to station, it should also get the token every once in a while. Similarly, if a token or if a station disappears from the bus, for example, when it's switched off, then somehow a station that would have forwarded the token to that neighbor should now be able to forward it to the next neighbor, to that neighbor's neighbor. And we don't have the simple solution that we had with the token ring, where you were at the wiring hub that simply bypassed the disconnected station. So all sorts of interesting challenges to sort out there. However, we're not going to discuss them. For those who are interested, it makes for really interesting reading. We should also note that the token ring topology is a ring topology that works very well in a local area network, in what is considered to be a relatively small area. When one scales up, when one begins to think about, let's say, a metropolitan area, where this ring becomes 100 kilometers long, or even longer to travel around the ring, then it becomes very wasteful to have only one message traveling around the network. And one of the protocols that we will not discuss, but that you can just take note of, is FTDI. And there you have a ring, And the token becomes something more like a slot. So one way of visualizing that, one way of thinking about that would be like something that is like a train that travels around this network. And in every car, it may have data or it may not have data. And when this train comes via your station, if the car is empty, then you can put your data into that slot, into that car, and it will travel around, and then you can remove it again. So multiple messages on this wire following the one after the other, and rather than the token, you're looking for an open slot into which you can put your data. However, as I said, we're not going to discuss that in any detail. Recall that various nodes in a specific area may be connected to one another via the same shared medium. It may be two computers that are connected via a single cable, or it may be computers that are connected to a bus, or it may be computers that share the same air around us to transmit waves, electrical signals to one another. Those computers that are sharing the medium somehow have to work together in a meaningful way. That includes, as we've noted on a couple of occasions, the ability to decide who can use that medium when, media access control or contention control. It has to decide how it will delineate messages. So somehow you have to mark the beginning and the end of a message, and also some certainty to know that a data message has been sent without any changes, that the integrity of that message is intact. And those were the three functions that we were going to discuss about the data link layer, about layer 2. We have now done that for most of the interesting variations, and we are ready to move down to the physical layer, layer 1, which we will begin to discuss in our next video.
Music